Hello, this is Callan Bentley. Welcome back for another pre-lab video. You are getting ready now for a very exciting week in lab. This is the week in lab where you establish some of the basic ideas about how we figure out how old rocks are, both in terms of their relation to other rocks, and then also in terms of basically assigning a numerical date to those rocks. This is really cool because once you master these skills, you're able to get out there in the real world and figure out what happened and when it happened. So we've got a couple of basic principles that we use when we are thinking about how old rocks are. The first of them is the principle of superposition, which says in layered rocks that form on the Earth's surface, such as sedimentary rocks and also volcanic rocks, the ones at the bottom are the oldest, and then the ones at the top are the youngest, because these things are forming on Earth's surface. So this applies to any layered rock, such as a sedimentary rock or a volcanic rock, but it wouldn't apply to something like a granite that intrudes from below. Another key principle that's illustrated here is the principle of original horizontality. The layers depicted in this block diagram are horizontal, which is how they form, more or less. And if we find them in some position other than horizontal, that suggests that they have been tilted or deformed, rotated since the time of their original deposition. One other concept that is conveyed here is that certain fossils basically can serve as timestamps on the rocks which include them. So for rock layer C here, for instance, to contain this particular fossil, it must have been deposited when that organism was alive. Another principle that we'll use is the principle of lateral continuity. This is a kind of common sense applied to geology here. If we find a situation like a canyon out west where we find a limestone down as the lowest layer on both sides of the canyon and a red shale above that, and then a nice yellow sandstone above that, that would not require two separate stories to tell, say, the story of the left side of the canyon versus the right side, because it doesn't take a whole lot of imagination to basically imagine the situation before the canyon was there, before it cut into what used to be three continuous layers stacked one on top of the other. Another principle that you'll be using this week in lab is the principle of relative dating by inclusions. I like to refer to this as the raisin bread principle because you can't make raisin bread unless you already have raisins. So here you've got a rock unit A and you've got a rock unit C. There's also an ancient erosional surface, an unconformity, which we'll talk more about here in just a moment, and that's labeled as B. But the key thing here to understand with regard to inclusions is that there are pieces of rock unit A included in rock unit C. You can't break off a piece of something unless it already exists. So in this case, you know that for sure rock A has got to be older than rock unit C. Otherwise, there's no way for younger C to include pieces of older A in its makeup. This diagram here illustrates a couple of principles. One is that principle of original horizontality. So rock layers A, B, C, and D here would have originally been deposited horizontally. And then at some point after they were deposited, they got folded, all right, probably due to some sort of tectonic stress squeezing these rocks from the side. That folding may have been accompanied by uplift, which encouraged erosion. So you've got that erosional surface there labeled E. That's another unconformity. And then sometime after that, sedimentary deposition resumed at the site with layers F and G being deposited on top of that. The other key principle that is being illustrated here, though, is this. There is an igneous dike that cuts through layers A, B, C, D, F, and G, and that dike is labeled as H here. You'll notice that there's contact metamorphism on either side of the dike where the hot magma that squirted into that fracture cooked the rock immediately adjacent to it. And you'll also notice that dike H cuts across, say, the unconformity surface, E. So therefore, that dike must be younger than the unconformity. It also cuts across all the rock layers that we've mentioned, so therefore that dike, H, has got to be the youngest thing in this diagram. One way of summarizing the principle of cross-cutting relationships is that the cutter is always younger, so whatever's doing the cutting has got to be younger. Here's an example of that, just looking at some igneous and metamorphic rocks, no sedimentary rocks at all. So here, basically, you had an original rock, which was metamorphosed to make rock A. We typically show metamorphic rocks with these little squiggly lines. And then that was intruded by this rock B, and you can see that zone of contact metamorphism where B is touching A. And then sometime after B crystallized, then C came along, and it cut across both B and A. So that'd be a way of working out the sequence of events here with crystalline rocks. One more example to illustrate this principle of cross-cutting relationships, and that is the prominent fault marked on this diagram. It's labeled as D. Here, the fault displaces layers A, B, and C, but it does not displace layer F, nor the unconformity E that separates F from A, B, and C. So we can basically establish the sequence of events here as the deposition of A, the deposition of B, the deposition of C, faulting of A, B, and C, followed by erosion to produce the unconformity E, and then the layer of sediment that's on top of it all, F. So these unconformities, I've mentioned them several times here, we probably owe it to ourselves to take a closer look at them. There are three kinds of unconformities that you need to know about: disconformities, angular unconformities, and nonconformities. And here's the difference between them. Well, actually, let's start off with what's in common to all three of them, and that is that all three of them have an erosional surface. This is a period of time that went by when rock was being removed at this site from the rock record, or at least it wasn't being deposited. So in other words, time is going by, but no new rock is being created. And as a result, we can refer to unconformities as gaps in the geologic record. They record the removal of information rather than the addition of information. So a disconformity is the first one we want to take a look at here. Disconformities are situations where we have these erosional surfaces separating sedimentary layers or volcanic layers that are more or less parallel to one another. So here in this situation, we've got three disconformities shown in this diagram. So rock unit A had to form first, and we know that because it's on the bottom, so superposition tells us it's probably the oldest. But also you can see here there's a piece of rock unit A included in rock unit C. Erosional surface B separates the two, and it looks like C is a volcanic rock because I see evidence of contact metamorphism here where C is touching A. Then it looks like rock unit E got erupted on top of C. There are pieces of C in E, and again there's contact metamorphism where E touches C. Finally, some more time went by, there was some more erosion producing unconformity F, another disconformity, and pieces of rock unit E were included in the overlying rock, which is called G. So basically here you've got a period of deposition followed by a period of erosion, another period of deposition, in this case a volcanic unit, more erosion producing unconformity D, more deposition, more erosion producing unconformity F, and then more deposition. So we've got a real switch going back and forth here between putting new rock material down at this location and taking it away. Okay, so that's a disconformity. Now let's take a look at a nonconformity. The definition of a nonconformity is it's an erosional surface below which there are no stratified rocks. There's no sedimentary layers. There are no volcanic layers. Instead, what you have are crystalline rocks, metamorphic rocks, and igneous rocks. So unconformity C here would be an example of a disconformity because below it we see this metamorphic rock labeled A, and we see an igneous rock labeled B. There's also another igneous rock over here, F, and that F cuts across unconformity C as well as A and the overlying layers D and E. So in this diagram, F would be the youngest thing. Final kind of unconformity is the easiest one to recognize, and that is an angular unconformity. Angular unconformities are quite visually striking because they have tilted, in other words, non-horizontal sedimentary layers below, and then horizontal sedimentary layers above. So in this circumstance here, A would be the oldest because it's on the bottom, followed by B, C, and D. Then there was a period of tilting, and that was accompanied by erosion, or it was followed by erosion. And then a new layer was deposited, F, on top of that. And you'll notice that F contains pieces of D and C and B in it. All right, so the principle of relative dating by inclusions tells us that F has got to be the youngest. Let's now go to a couple of my students and have them explain this concept. Janelle and Kristen, take it away.
So I totally don't get this angular unconformity.
Well, to get the difference between B and A over here, B had to be horizontally deposited and then folded, then you wrote it away, and then A was deposited horizontally on top of B.
Okay, so now, based on that demonstration, I hope you have a better sense of how angular unconformities form. There is one other thing in this diagram that we should probably talk about, and that is the fossil content here. You can see that there are diagrams of key fossils in certain layers, and we can use that information to figure out when those layers were deposited. These are index fossils, and there's a diagram in your lab manual that shows the geologic range zones for these different organisms. So what you're looking at here is not necessarily the picture of the organism, but the little black lines that are next to these organisms. Those show the range zone, and that basically means that that's when that organism was alive. So for instance, sharks that you see right here first show up in the geologic record in the Devonian, and of course they last until the present day, so they have a very long range zone. On the other hand, this organism down here, L-Rathia is a trilobite, and you can see that it has a very short range zone that begins and ends in the Cambrian period of geologic time. So if you find a shark in a rock, that basically tells you that that rock could be Devonian, or it could be Mississippian, or it could be Pennsylvanian, or Permian, or Triassic, or Jurassic, or Cretaceous, or Paleogene, or Neogene, or Quaternary. On the other hand, if you find L-Rathia in a rock, that can only be Cambrian. So L-Rathia is a better index fossil for figuring out how old that particular sedimentary deposit is. So here's how this works with our angular unconformity diagram. We've got 4 fossils here, and we go and we look at that diagram and we find the range zone to figure out how old they are. So for instance, down there in layer B, we have this organism. That is Flexicalamine, and you can see that Flexicalamine lived only during the latter part of the Ordovician period of geologic time. So layer B must be Ordovician in age. Layer C contains fossils of Phacops. All right, so Phacops is an organism that first shows up in the late Silurian and lasts until the end of the Devonian. So that layer could be either Silurian or Devonian based on the presence of Phacops in its strata. Next one up is this brachiopod Conetes. And Conetes, it looks like, is not particularly great as an index fossil because it spans the Silurian, Devonian, Mississippian, Pennsylvanian, and the Permian. However, all of those are within the Paleozoic era of geologic time. So if you find a rock unit with Conetes in it, then that tells you that's got to be a Paleozoic rock. Finally, up in the layer on top of the unconformity surface, we have leaves of Phagopsis. That is a plant leaf, and you can see that it's restricted to the Paleogene period of geologic time. So this allows you to put some age constraints on your overall relative dating of the different geologic units. Another way that we can do more precise dating of the individual rock units that we're talking about is with certain rocks, usually igneous rocks, but also some metamorphic rocks, we can do dating of the crystals that form and make up that rock. So there are not a whole lot of mineral crystals that are suitable for this sort of a treatment. You can see here in the middle part of this table diagram here, it lists some of the different materials we can date. For carbon-14 dating, we can use shells, limestone, and anything that is organic. For potassium-40, argon-40 dating, we've got biotite, muscovite, the 2 micas, and then also volcanic rocks if we just grind up the whole volcanic rock. And then 2 of the most powerful dating techniques, uranium-238 and uranium-235, both rely on a mineral that's not extraordinarily common called zircon. However, even though it's not a big, bulky constituent of igneous rocks, it is present in many igneous rocks, and it can help us figure out how old they are. So the idea here is that you have unstable radioactive atoms. These are called parent isotopes. And over time, they go through a process of radioactive decay, which generates energy and basically produces stable new atoms that are called daughter isotopes. You start off when you have a newly formed crystal. The structure of that crystal is such that it happily incorporates the parent isotope, but it will actively exclude the daughter isotope. As time goes by, the daughter isotope is produced through radioactive decay. It's shown here with these red dots. And as those red dots accumulate, that basically is an indication that that crystal is older. The amount of time it takes for half of the parent to decay, in other words, 50% parent left and now 50% daughter, is referred to as one half-life. And the amount of time that a half-life takes depends on what isotope we're talking about, whether it's uranium-238 or uranium-235 or potassium-40 or carbon-14. They all have different half-lives. One half-life of uranium-238 is worth 4.5 billion years, whereas one half-life of uranium-235 is worth only 713 million years. In other words, uranium-235 is far less stable than uranium-238. It falls apart more rapidly. So the idea here is that you look at the proportion of parent to daughter. Say you have 25% parent and you have 75% daughter. That indicates that 2 half-lives have passed. And if 2 half-lives have passed, then you need to multiply that by the length of a half-life, okay, the material in this column. So say we're dealing with potassium-40, argon-40, and we've got 25% potassium-40 and 75% argon-40, indicating 2 half-lives have passed. We need to multiply 2 by 1.3 billion years. So we end up with 2.6 billion years. There's a table in your lab manual that explicitly links the percent of parent isotopes to daughter isotopes, and then basically translates that into the number of half-lives that have gone by, and then gives you a nice simple formula for calculating the age. So let's look at an example of how this would actually work in real life. So here we are in Google Earth. We're looking down on the North American continent, and if we zoom in here, there's a place I want to show you in Wyoming. You can see I've got a place mark on it here, but basically this is where the Wind River has its headwaters here in the Wind River Range, which is this range of mountains down here in the southwest. And you can see various tributaries flowing northeast out of the Wind River Range, merging together. They're dammed here to make a reservoir just south of the Owl Creek Mountains. The Owl Creek Mountains run east to west across the picture. And if we zoom in here, we can see that the Wind River cuts across the Owl Creek Mountains, and in so doing basically has exposed a pretty amazing unconformity there. So what we're going to do is we're going to zoom in to that unconformity and look at it as if we would while we're on the ground. What we're about to look at here is what's called a gigapan image. And it's an image that I took out there with a camera that basically takes a very high resolution image. You can see there are 3 main geologic units here. The first is this dark colored stuff here in the middle, and that dark colored stuff is a gneiss. That gneiss is cut across by this massive pink stuff without layering, without foliation, and that pink stuff, you might guess, is a granite. You'd be right. So both the granite and the gneiss then abruptly stop, and they're overlain by another unit, and that other unit is a sandstone. The sandstone is the Flathead sandstone. It's a very extensive unit across the entire area. You can actually zoom in here and see some cross-bedding here in one of those layers as well. The Flathead sandstone includes fossils of this organism. That is a trilobite called Olanellis, and it'll be a useful index fossil for figuring out how old the Flathead sandstone is. Okay, so with our Wind River Canyon location, we've got a gneiss, and then cutting through that gneiss is a granite. Let's say we do isotopic analysis on zircons that we extract from that granite. And we find that as far as uranium-238 to lead-206, we have a ratio of about 7:3. So in other words, there's about 7/10 parent and 3/10 daughter. So if you look at this chart, the percent of parent isotopes, and come down here and look for something that is close to 7, 70.7% comes pretty close, and 29.3% daughter is pretty close to 3/10. So that indicates that half of a half-life has taken place. So in other words, not even one full half-life. And the way we would calculate the age is to multiply the half-life of that isotope by 0.5. All right, so the half-life of that isotope is 4.5 billion years, and that 4.5 billion years is then cut in half, and we end up with 2.25 billion years for the granite. Obviously, the gneiss is going to be older than the granite because the granite cuts across the gneiss, so the gneiss would be older than 2.25 billion years. Then, of course, there's the erosional surface, the unconformity, and then above that unconformity we had the flathead sandstone, and that flathead sandstone included fossils, we said, of Olanellis, the trilobite. And you'll recall from the diagram of the geologic range zones in your lab manual that Olanellis is a Cambrian-only organism. Basically, that unconformity surface separates 2.25 billion-year-old rocks from rocks that are approximately 520 million years old. So there's a whole lot of time missing along that erosional surface. That unconformity is representative of a tremendous span of missing geologic time. Okay, so those are the key ideas for figuring out the sequence of geologic events, and I hope you have a great time solving these mysteries this week in lab. Thanks a lot for your attention. See you next week.